Okay, hello all. Good evening.
Good evening, sir.
Yeah, am I audible clearly?
Yes, sir.
Yes, right. Okay.
Yes, sir.
Okay. So, how are you guys? It's been a while. How is Max One going on? Hmm.
So far
Anyone?
going good, sir, but time is bit less for maintaining all four.
Okay. And how is calculus?
Good, sir. Going good.
Good. Okay. So, yeah, today we are going to uh, whatever we are going to look into is of week 10. Basically, it's of graph theory. So, any session happened before regarding week 10,
No, sir. This is
or
first
this is
session, and
this is the first session?
yeah. Before taking doubts, sir, can you give a little glimpse about week 10? Because haven't gone
Hmm.
through all lectures.
So my next question is that. So how many of you have gone through week 10?
Half of the week.
You can, okay, at least started
Yes, sir.
looking into contents. You can raise your hands. So I just wanted to know how many of you have gone through week 10. Not completely, at least started looking into lecture 1, lecture 2, solving some activity questions. Okay. So very few out of 22, maybe 5, 6 I can see. So others preparing for quiz 2, is it?
Yes, sir. We have.
Yes, sir.
Hmm. In that, then Wednesday is the deadline, right? Week 10 ka?
Yes, around 16, I think.
Hmm. So within 2 days, will you able to cope up, or
Not
are you
so
going
well.
to leave week 10? Okay. So my suggestion is just go through week 10. So it will be very interesting and it will be challenging too. Okay, graph theory. Many of you have not seen earlier, I guess. So
In
this is
computational,
one.
we think.
Okay, in computational you might have seen, but for the guys who are taking maths 1 first and have not done anything related to graph theory in school, so for you guys it will be very interesting for the very first time when you see these things. So I recommend at least spend some 1 hour or 2 hours before you go to quiz 2. Just open and look into lectures. So I'm pretty much sure that once if you open week 1, week 10, lecture 1 and 2, so it will automatically thrive you to look into 3, 4, 5, and so on. Hmm. So okay. So you can down your hands.
Sir, practice assignment answers are uploaded. CT was uploaded.
We have found that error. We will replace it with max
Okay,
practice.
thank you.
To put quizzes after respective syllabus. Yeah. See, the thing is, every term we used to have like that, but only this term it happened like while week 10 is going on, we are getting quiz 2. So same thing happened for quiz 1 also. So after week 5, so you have to give quiz 1. So this is the only term it happened because of TCS. See, TCS is conducting many exams other than this also. So even we have to get perfect time slots from TCS also. So there is some clashes with TCS other exams. So that is why we had to postpone few things. Okay. Okay. So then we will do one thing. So those who haven't seen week 10 and those who have seen week 10 also, what I will do is I will quickly give you some summary kind of thing. I will try to finish it in this 1.5 hour, 2 hours gap. And on Tuesday, so tomorrow, you have solve with us session, right? Please do attend that solve with us session also, so that you will get an idea how this graph theory is going to be. And then if you wanted to look into these things, just spend Wednesday on week 10 and submit the graded assignment. Then from Thursday, you start preparing for quiz. So I know 3 days will not be sufficient, but give some time to week 10. Okay, so let me share my screen and okay. So is my screen visible?
Yes, sir.
Yes, sir.
Journal screen, graph theory week 10, right?
Right, sir.
I have shared that
Yes, sir.
screen, I hope. Yeah. Okay. So let me zoom it a bit. Yeah. So if you see in maths 1, we have 3 subparts. So part 1, we have learned about set theory, then functions and everything. So we have studied till logarithmic functions. Then the next part is like calculus part, which is from week 7 to 9. And the final part is graph theory. So for graph theory, we have 2 weeks. Okay. I recommend everyone please be on mute unless if you have any doubt. Okay. Yeah. Thanks. Okay. And the last part is graph theory. And this graph theory is for 2 weeks, week 10 and week 11. So in week 10, we will start with the basic definition of graphs and we will see what are the different types of graph. Don't think that the graph theory is somewhat related to this graphing, polynomial graphing or anything else. So this is nothing related to that. This is a new branch in mathematics, another branch in mathematics, and recently emerging branch in mathematics. So if you wanted to do research in mathematics, then I suggest you to pick graph theory because very less study has been done on this part. Okay, from mathematics side, okay, not from the electronic side. So you might have seen in CT, you might have seen graph theory in one way, and this is mathematical graph theory. We more focus on graphs, okay, not on the coding part. So we will look into this, the types of graphs and what is path, and then we will look into few terminologies of graph theory. So you have to be very clear about these terminologies because we are going to use these terms more often in graph theory. So this reachability, graph coloring, minimum vertex color, cover, maximum independent set. So you should be able to know all these things. And don't think these are very new things which are not understandable. In this, I'm telling you, graph theory will be very interesting part. Okay, just a second. Just 1 second. So give me 2 minutes. Okay, my pen is not working properly.
Hello, show.
Hmm.
So I facing problem with Riemann sum means in question, sir.
Hmm.
Would you tell me, sir?
Riemann sums, is it?
Yes, sir.
Okay. So can you wait for a couple of maybe 1 hour? We will discuss this week 10. Then I will come back to week 9. Is it
Okay,
okay?
sir. Okay, sir.
Because this week 10 is completely unrelated to week 9. So there will not be any big issue, I hope. Hmm?
Okay, sir. Okay.
What has happened?
Hello?
Yeah, hello.
Sorry, actually, I could not hear anyone.
Ha. See, my pen is not working properly. I'm trying to fix it.
All right.
I don't know. It stopped suddenly. Okay, anyway, uh, if needed, I will try to write it here itself. Okay, so let us start without any further delay. Okay, let's see. So today we will be covering these things. So these are the terminologies of terms involved in this graph theory topic. So you might know few, but maybe few things are very new to you. So we look into this maximum independent set, then we will look into what is matching, and then we will look into another topic in graph theory, which is adjacency matrix and adjacency list. And then we will try to look into what is degree of a vertex, and then what is this BFS, DFS. So what are these searches and why are they useful? And then DAGs, which are called directed acyclic graphs. So we'll look into that. And finally, the last topic in week 10 is topological sorting. So these are the topics that are present in week 10. So week 10 is very uh, large and it consists of maybe, I guess, 3.5 hours content, only content. So once if you start looking into the contents, you will enjoy it. Okay. We will start one by one. Okay. So before that, what is graph? So can anyone tell me from CT who has attended what is a graph?
That contains edges and nodes.
Hmm.
And helps us understand the relation between them. We can study a particular kind of relation and represent it visually between different elements in a particular set.
Hmm. Okay. Any simple.
So graph
Hmm.
is a bunch of nodes and their relationship presented in the graphical way.
Hmm. Okay. So I accept whatever you guys said. So graphs are basically made up of nodes, and so we say vertices. Okay. So in mathematical graph theory, we used to call them as vertices. Vertices and few edges which are connected between vertices. Okay. See, I'm completely sorry for I'm not able to write. So basically the graph will be like this. So like this. So you see here. So these are called vertices, and the edges connecting these vertices. So the lines connecting these vertices are called edges. And the graph is made up of these vertices and edges. And we will define these vertices and as well as the corresponding edges. And we will make and create the graph. So that is what graph is. And there are different types of graphs. So you just look into this. There are cyclic graphs, connected graphs, okay, planar graphs, and there are trees are also different types of graphs. Okay, what we require is basically we require only few things: cyclic and acyclic graphs, and another thing is connected and disconnected graphs. So try to understand what are the cyclic and acyclic graphs. And also one more important thing is trees. So we will look into these trees in deep in week 11. Okay, so graphs are basically made up of vertices and edges, and each vertex may be labeled or unlabeled. If it is labeled, we will label it like this. So this, if you see here, so this vertex is labeled with v1, labeled as v2. So these are called labeled graphs. If I didn't label at all, if I remove this v1, v2, v3, and everything, then that particular graph is called unlabeled graph. Okay, so so there are different types of graphs. You open the lecture and look into the different types of graphs. So I don't want to go in deep in that. So you can understand it easily. I wanted to discuss more topics which are pretty difficult to understand. So we will start with path. So path is also a different type of graph. A path means a path is actually a sequence of vertices v1, v2 to vk connected by edges. So in a particular graph, so let's take this graph itself. So if I wanted to traverse in the graph, traverse means going along the graph, along the edges. So if you look here, so I started from v1. Treat like you are at v1 now. So you have an edge to go. So it's like a road. So you can traverse or you can use this road to reach v2. And from v2, there is another edge that is connecting v3. So from v2 to v3 you can go. And if I collect this v1, v2, v3, and so on to vk minus 1, vk. So I look at this path. So even the English meaning of path is actually where we can walk, road kind of thing. So here also the same meaning. So path is actually connecting vertices. So you see here v1 is connected to v2. So I can go from v1 to v2, v2 to v3, v3 to v4, and so on, like vk minus 1, vk minus 1 to vk, like this. So this is a path. So the path is v1 to v2, v2 to v3, like this. This is the path. So how we write is like this: v1. So path is represented like this. So I'm using my mouse to So and so on.
Sir, maybe restarting your system will resolve the issue.
Uh,
Yes, sir. We can wait because teaching without pen is like
yeah,
Sir,
yeah, yeah. Even I
will
don't
not
like.
connect that much.
Okay, okay.
Sir,
Just
remove battery and put it again, sir. It will help, I think.
no. See this tab, Wacom tab is not connecting properly. I think the wire is problem.
Sir,
Maybe I
what I
will
mean, what I'm saying is remove pen battery.
pen
There
battery.
is no
It's
battery
not
in
about
Wacom.
There
pen
is no,
battery.
it's Wacom
There,
tabs
there
is
is
talking.
Wacom
there is
tabs
no
too.
I am
battery in
using
Wacom tab.
Wacom
I don't know.
one by Wacom.
Okay.
My Lenovo tab have.
So we have one software regarding this. Before that, we have to install.
Acha. So right now it's not possible. Arre.
I'm also using so the Wacom. We have one software we have to install before we have to use.
Mm-hmm. No, it worked till now. It worked. So I have written this whole notes before this
Okay.
session only.
Okay.
Till now it is
So
working,
maybe
but
restart
sudden.
will work. We can wait.
Oh, okay. Maybe I will just restart and come back. Just give me 2 more minutes. Not 2 more minutes. 5 more minutes. Okay. And I am extremely sorry for this.
This topic is most important, sir.
Okay. Okay. Just give me 5 minutes.
Okay, sir.
Yeah. Hello. Am I audible?
Yes, sir.
Yeah.
Yes.
So got it.
Yes, sir, you're audible, sir.
It worked. It worked. Thanks. So I got my tab. Sorry, welcome. So give me one more minute. I asked them to make me co-host again. Let me share my screen and we will start quickly. So it's already in 15 minutes delay. So okay, so let me just recap again what we have discussed till now. So graph is basically a pictorial representation. So it's a pictorial representation of any data in an ordered way, organized manner. Okay. So it's basically consists of vertices and edges. Okay. So vertices, we will denote it as some circle. Inside that, if I name that vertex, if I label that vertex, that is called as a labeled graph. If I didn't label at all, it is called as unlabeled graph. Okay. So what is that what? Shalini SK. So is it related to the topic or? Okay. Okay. So that is graph, and see, you might have learned vertices as nodes or points or vertices all are same, but in different textbooks it will be used in different ways. They will be referred as different names, and also edges, lines, connections, and these are all refer the same. Okay, so it's our way to call it. Oh, what is it delay? No, just give me 2 minutes. Let me get the co-host access. And there are different types of graphs. Okay. So out of this, today we will be discussing the undirected and directed graphs mainly. Hello. மறுபடியும் ஒரு வாட்டி co-host பண்றீங்களா? Okay. And there are, when you look into the lecture, there are many other types also. Complete graph, planar graph, acyclic graph, cyclic graphs. So you have to go through all these things. So what are these things? Just the definitions. So they are just the different types of graphs. If it follows some property, then that graph is called as that type of graph. Okay, we will start looking from path. What is a path in a graph means? Okay. Yeah. So as we just now discussed, let me again redefine what is a path means. So a path is basically a sequence of vertices v1, v2, v3, and so on, vk, connected by edges. So those vertices need to be connected by an edges. So if you see here,
So
so
your
this
screen is
v1,
not visible.
oh sorry, now
Yes, sir.
Yes, sir.
yes, okay. So a path is a sequence of vertices which are connected by edges. So if you see here, so v1 is a vertex and that is connected to v2, and v2 is connected to v3. As I already said, so when you are at one vertex, treat like you are at that particular vertex point. So now you have a possibility to reach or to go to vertex v2. So treat it like another point. So it's your home and you wanted to reach to one more other place. Treat it like that. So these vertices are junctions and these edges are the paths. These edges not path. These edges are the lines or roads. So you see here v1 from V1 you can go to V2. So from V2 you can go to V3. Like this, from V3 you can go to some other vertex. So like that you can reach Vk minus 1, and from Vk minus 1 I can go to Vk. So what I can say is, if I start from V1 I can go to Vk. So that means I will say that there is a path from V1 to Vk, and that path is denoted like this. So V1, V2, V3, V4, and so on, Vk. So this is a path. This is a path from V1 to Vk. Okay. So a path is nothing but a sequence of vertices which are connected by edges. So now we will look into what is reachability means. So what is reachability? A vertex V. So now a vertex V is reachable from vertex U if and only if there is a path from U to V. Okay. So understand this. So if there is a path from vertex U to vertex V, then I will say that vertex V is reachable from vertex U. So that means you are at vertex U point now, vertex U, and now you wanted to go to vertex V. You wanted to reach to vertex V via edges. So if there is a path, then you can reach. If you can reach, then the reachability exists between vertex U and vertex V. Okay. So this reachability refers to finding a path to reach from one vertex to another vertex. That's it. So now the questions can be like, is D reachable from F? So is vertex D reachable from vertex F? So can you just look into this graph? Now let us take this graph.
No,
And
sir.
if someone asks you like from F, now you are at F.
Sir, can you
Okay.
scroll a bit?
Scroll where?
Scroll a bit down. We can't see D, point D. We can only see
It's
AB.
visible. It's visible.
It's visible, sir.
It's in the
It's
center of
visual,
my
sir.
screen.
We
Yeah.
can
Yeah.
zoom in.
Yeah, it's visible, sir.
Now the question is D reachable from F? So now you are at F. So by traversing through edges, can I go to D? Okay.
No.
So this particular graph is a directed graph. Directed graph and undirected graph. Difference between directed and undirected is if you see any directions to the edges. So like this. So this edge, if you see, this has a direction from A to B. So there is no backward coming edge from B to A. So if you see at least one edge like this, then that particular graph is called a directed graph. Or I can define undirected using directedness if every edge is bidirectional. So like this. So this is a bidirectional edge. So in my graph, if every edge is bidirectional, then I say the graph is an undirected graph. So we don't need any direction to the graph anymore, because it can, all the edges are bidirectional. So I can remove that directions, and I simply draw like this. So I will not show any direction to the graph, to the edges. So this particular edge without direction means it's a bidirectional. So I can go from B to F and F to B. Okay, so that's the difference. This is an undirected edge. So undirected edge, bidirected edge, both are same. Okay, undirected edge, and this is a directed edge. So this is a directed edge from A to B. So that is the difference. So from this edge, I can only go from A to B, not from B to A. I can't come via this edge. Okay, so that is the difference. So now tell me, is D reachable from F? So now you are at F. Can I go to D?
No, sir.
No, sir.
No.
No.
Okay. Why no? Because if I start from F, I can go to B via this edge. From B, can I go to any other place?
No,
No.
sir.
No,
No,
sir.
there are no edges going
No, sir.
from D. So I will be stopping here itself. So I can't reach D. Can I, if I ask like this, is F reachable from D?
Yes.
Yes.
Yes, sir.
Yes, sir.
Yes, sir.
Yes. So what
Yes,
should I
sir.
do? So what should I do? I should find a path from D to F.
No,
Right?
sir.
No.
D to F, right, sir?
So
Yeah.
if I wanted to check whether F is reachable from D, I need to check, is there any path that is going from D to F? So let's find out. So I am at D now. So I can't pick this side. There is no edge going from D, but there is an edge going from D to C on the left side. So from here I can go to C using this edge. So once I reach C, from C I can go to A, and from A I can go to B, and from B I can go to F. So there is a path from D to F. So what will I say? If there is a path from D to F, then F is reachable from D. So this is yes. Okay. So what if I ask like something like find all the vertices that are reachable from C? So the question is, let me take a new page. So the question is, find all the vertices that are reachable from C, from vertex C. So now I am at a vertex C point. So vertex C here, I am here. So to where all vertices I can go? So that is the question. So what are the vertices that I can reach from C?
D, A, B, F.
D, A, B, and F.
Yeah, D except E.
Yeah.
Sir, all except E.
All except E, correct. So now I am at C, I said. So from C, using this edge, I can reach D. So using this edge, I can reach A. So once I reach A, from A to B, I can go. So there is a path from C to B. So therefore, I can say I can reach from C to B. Again, from B to F, there is an edge. So I can also reach F. So except E, I can reach to every other vertex from C. And what if I ask, what if I ask, find the vertex from which every other vertex is reachable?
Is C. Okay, B, I
Okay.
think. Just graph.
So I will bring that graph down.
E only.
So now what you have to find? You have to find a vertex, that vertex from which every other vertex is reachable.
E.
E.
Sir, E.
So now I have to be at which position so that I can reach to every other vertex position. C anyway ignored because from C I can't go to E. So C cannot be. So from here we can check from D. So you pick one vertex from A. Where can all I can reach? From A I can reach only B and F. Nothing else. So A is also ruled out. From B I cannot go to anywhere except F. So again B is also ignored. So not C. It is not C. It is not A. It is not B. And from F also I can only come back to B. I can't reach to any other vertices. So F is also ruled out. So either it should be D or E. So you check D also. From D I can go to C. C, A, B, F, but not to E. So from D, I can reach to every other vertex except E. So D is also not the correct. So let's check E also. So if you check E, from E, I can reach to D. From D, I can reach to C also. And again, from here, I can reach to B. And once if I reach to B, again I can reach to F. and from C I can reach to A. So E, D, C, A. So I can reach to every other vertex if I am at vertex E. So the answer is it should be vertex E. So that vertex is vertex E. So these are the different ways in which we can ask you, right? Different types of questions we can ask you. So even if so, where this reachability is more useful. So let's take a real life example. So I just said vertex A, B, C, D. So I will just name it. Suppose there are some cities in India. Okay. So there are some cities in India, namely maybe Delhi, Mumbai, Chennai, Agra, and Bhopal, Gaya. Okay. And for E, Ernakulam. Okay. So these are some cities. So these vertices are the cities. And each of the city has an airport. Let's assume that it has an airport. So from here, how I will draw these edges is, now I am defining edges. Listen properly. So if some cities has a direct flight between two vertices, then I will give a directed edge from one particular vertex to the other particular. So for example, so let's say this is Agra and this is Bombay. Okay. So if I draw an edge like this, so that means there is a direct flight from Agra to Bombay, but there is no direct flight from Bombay to Agra. So that is what it means. So in real life, it is not true. I agree, but let's assume. Okay. So there is a direct flight from Agra to Bombay, but there is no direct flight back to Bombay to Agra. So you have to, if you want to reach to Agra, you cannot reach because from B, A is not reachable. Okay, like that. So in real life, so we will take this cities as the vertices, and we will try to plot this direct flights as the edges, and we will look whether one city how much efficiently I can reach to other city, or will I be able to reach other city or not. Okay. So or if I am in Chennai, if I am in some place where all other places I can go, and from which city, so the last question is, yeah, from which city I can actually go to every other places. So where can I get more number of flights to more cities? So like this. So these things. Okay. So this is about reachability. And next we will look into one more important graph theory term called graph coloring. So even this also has huge importance in some nowadays. Some data they are using this graph coloring only, and also if you wanted to do the scheduling and everything, this graph coloring is more efficient way to get the schedules done. So we will talk about real life scenarios. Let us understand what is this graph coloring first of all. So the name might look something different, but it is very easy. So what is this graph coloring mean is, so the graph coloring or vertex coloring or just coloring all refers to the same. So when we say vertex coloring, then there is another thing called edge coloring also, but we are not going to discuss in this particular course. We are only discussing about vertex coloring. Okay. So what is this graph coloring or vertex coloring is? So what that means is, you have to find the number of colors. So if I say colors, you know the colors, right? Red, blue, green, these are the colors. So we have to find the minimum number of colors required to color every vertex in a graph such that no two adjacent vertices have same color. So this adjacent means sharing an edge. So if two vertices are connected with an edge direct, if there is a direct edge between two vertices, then those two vertices are called as adjacent vertices. So here if you see here, so the C and A are adjacent vertices because there is a direct edge between C and A. And similarly, this E is adjacent to vertex C, vertex D, and vertex B. So this is what adjacent vertex adjacent means. So adjacent means sharing an edge. So what we have to do in this graph coloring? So we have to find minimum number of colors. So you have to color every vertex first of all, and once you color that vertices, if two vertices are sharing an edge, they shouldn't get the same color. So this is like a puzzle. So you can treat it like a puzzle. So you start giving colors to vertices such that no two adjacent vertices have same color, and you have to minimize this usage of number of colors. So I can give all here there are some 7 vertices. I can give all 7 vertices 7 different colors. So that is also a coloring. But what we have to do, we have to give the minimum number. We have to use the minimum number of colors. Okay. So just try, give it a try. So this doesn't require any prerequisite. Just now whatever I have explained, you can use that. So try to give colors to each and every vertex and find. So you have to decrease the usage of number of colors. You have to minimize the number of colors.
4.
Okay, 4.
6.
Any other options?
So 3.
3.
3.
Yes, sir.
3.
3.
Okay. Anyone less than 3? Okay. So as I already said, let us start with one vertex. You start coloring one vertex. Let us start with giving red color. Okay. So my first color is red. So from where will we start? So let us start with vertex A. So you start from any vertex, it doesn't matter. So vertex A, I have given red color. So once I have given vertex A red color, I cannot give that red color to vertex C. I cannot give that red color to vertex D as well as vertex B because they are adjacent to each other. So the remaining vertices are E, F and G. So from E, F and G, if I give it to F, so if I have given it to F, then I cannot give to E and G, correct? So what we can do is, so try to give the first color to the maximum number of vertices possible. So if I have given it to E, okay, then I can give that same red color to G also. And now if you see, I cannot give red color to C, red color to D, F and B. I am done giving colors. I cannot give any red color to any of the vertices. Now change the color. So now next take a new color, second color, maybe color 2. Okay. Now color 2, you start giving color 2 to any of the vertex. So
C.
you can give to okay, C. So you can give to C. So once you give that red color, green color to C, I can give that green color to D also. Again, here if you see, if I give that green color to F, okay, if I give that green color to F, and again it blocks D and B to take green color. Again, try to give. So our agenda should be using minimum number of colors. So once I pick color 1, I will try to give color 1 to maximum number of vertices possible. And then color 2, and even that color 2 also I will try to give it to maximum number of vertices possible. So here if I have given it to F, what happens? This blocks D and B. But if I hadn't given to F, instead I have given to B, then I can give that same color to D. Yes, correct. So now by using only 2 colors, I have already colored 6 vertices, and I am left with only one vertex to be colored. This F cannot be colored with red because G is an adjacent vertex, and this F cannot be colored with green because D is an adjacent vertex. So this has to take a new color. So the third color is blue. So this is how you have to do the coloring. So the minimum number of colors required to color this graph is
3.
3.
3. Okay. So the vertex coloring is equal to 3. Okay. This is what graph coloring is. Okay. So try solving few problems. Take some random graphs you like and try to give the coloring to the graph. So start with one color. Try to give as many vertices as possible and then go for the next color. Likewise. Okay. And there is one important property or a deduction. So that is called as a theorem also, 4 coloring theorem. So even this is also not discussed in the lectures, but anyway, it's very good to know. So if I have any planar graph, okay, planar, I mean, explain the planarity also. So I will take 2 more minutes to explain this planar graph, because this is also an important type. So planar graphs are different types of graphs where the edges intersect only at the vertex points. Okay, only at the vertices. So if I take an example, so see this. So this edge and this edge, they both are intersecting at this point. Okay. So now what I have to do is, if I can redraw this graph such that these two edges will not intersect at all, or they will intersect at these vertices points. So if I can redraw it, so if I have redrawn this and this graphs are both are isomorphic graphs. So both have 4 vertices, both have 6 edges. So it's basically a complete graph. Complete graph, again, complete graph means, so how many vertices you have, you add edges between all the possible vertices. So you just pick 2 vertices, add an edge. So you just complete the graph. Okay. So it will have all the possible edges between 2 vertices. Okay. If I can redraw this graph, then this graph, so now you can see this graph. If you see this graph, the edges are meeting at only at vertex points, and nowhere they are intersecting. So all the edges are clean, they are not intersecting in between. Okay, these kind of graphs are called planar graphs. Okay, so within a plane I can embed them. So within a plane I can draw it like this. Okay, and there are graphs called non-planar graphs. Again, this is a complete graph with 5 vertices. You can check, if you pick any 2 vertices, there will be an edge, direct edge connecting to it. So this is called K5. So complete graph with 5 vertices. So now if you see this K5, see there are so many intersection points. And even though if I try to rearrange the graph, redraw the graph, so see I can draw it like this. And now I have to join these two. So these two, if I have drawn like this, and these two, if I have drawn like this, now I am left with these two vertices. So this and this. Okay. So I cannot draw like this because this will intersect this edge here. So I cannot draw like this because again there will be an intersection point, or I cannot draw like this because there will be again an intersecting point. So now you can see this graph, however this K5 complete graph, in any possible way if I draw, there will be at least two edges that are intersecting in between. So these kind of graphs are called non-planar graphs. So which fails the property of planarity. So they are called non-planar graphs. So planar graphs are these graphs. So we have to draw the graph in such a way that the edges will intersect only at the vertex points and not in between. Okay, understood?
Yes, sir.
Yes, no, over
Yes,
the
sir.
head, no, right?
Sir, I got it. Sir, may I clarify?
Hmm.
Sir, even though apparently the edges may be intersecting, but if a graph can be represented in a way that the edges don't intersect, it's a planar graph.
Yeah.
But if it is not possible to represent it in such a manner as you have presented here, then it's a non-planar graph. And
It's a non.
this complete graph is not a category of non-planar graphs.
See, from K5 it is non-planar. So complete graphs from 5 vertices. So 5 vertex, 6 vertex, K5, K6, these are all non-planar. K4 is a planar. So this is K4. And this can be drawn like this. Okay, K3 is a planar. So complete graph with 3 vertices. Okay. So from K5, all the complete graphs are non-planar graphs.
Okay, thank you, sir. I got the earlier part wrong.
So now what I am going to say is planar graphs. If I have a planar graph, so a planar graph can be colored using maximum of 4 colors. Okay. So if you wanted to make a guess, okay, time is running out and the graph which you are seeing on the screen is planar directly, no need to rearrange or anything. So if you are seeing a graph which is a planar graph, and if we have asked you to use the graph coloring, so if you wanted to make a clear cut guess, then definitely you should be guessing less than 4, less than or equal to 4. Okay, don't be like if you have given 5 or 6, it will definitely go wrong because a planar graph can be colored by taking at most 4 colors. So that is a theorem, and that's a great theorem that is proven in recent years. Okay. Initially it was 5 colored theorem, so 6 colored theorem. Then later on it came to 5. Then recently it turned out to be 4 color theorem, 4 coloring theorem. If you are interested, you can open Google and go through that 4 color theorem. Okay, so that is about graph coloring. So graph coloring is basically how to color all the vertices such that no two adjacent vertices will have the same color. Now let us see what is this minimum vertex cover means. From the name itself, you can deduce few things. Vertex cover, so it is related to vertices. Okay, and there is something called minimum. So we have to look at the minimum possible thing. So those are the two things you have to understand. Minimum vertex cover. So what is this? Minimum vertex cover is. So what we have to do is, again, so this is also a term in graph theory, and this minimum vertex cover means you have to find, so we have to find again the smallest subset of vertex set. So again I said, so this is related to vertices. So vertex cover is related to vertices. And what I have to do, I have to find the smallest subset from the vertex set. So let's say V dash is the smallest. So V dash is the vertex cover. And that vertex cover is actually a subset of vertex set. Okay. So I have to pick some vertices. Okay. I have to pick few vertices. How I should pick those vertices? Such that it covers all the edges in the graph. So it covers all the edges in the graph. What does this mean? So what is this covering means? So when I pick a vertex, so let's say if I have picked A, vertex A. So then covering means this vertex is an endpoint. So edge has two endpoints. So two vertices, and treat it like two endpoints. So if I had taken vertex A, if I had selected vertex A, this vertex A covers this edge, this edge, this edge, because for all these three edges, vertex A is one end point. Okay. So once I pick vertex A into my vertex cover, so that vertex A will cover this edge, this edge. So the edge AC, edge AD, edge AB. Okay. So now I am using I will be using some mathematical notations to denote this vertex cover. So vertex cover, so I already said V dash, right? So V dash, and let me take E as the edge set. So E refers to edge set. This edge set contains AC edge, CE edge. So all the edges in this vertex, sorry, all the edges in this graph, CE, EB. So whatever the edges are there, FG. So all the edges. Now observe carefully this vertex cover. So okay, and V dash is the vertex cover, I said. Okay, now if I look at the intersection between two sets, okay, V dash intersection I, so vertex I, where I comma j belongs to edge set. Okay, this is one set. This consists of all the edges, starting points of all the edges. So if I look at the intersection between V dash along with the edges, this should be non-empty. Okay. So understand it clearly. So whatever edge I pick, so this simply refers to whatever edge I pick, at least one endpoint should be there in my vertex cover. So that is what it means. So if I have intersected with any I, which is I comma j is an edge, so this I should be in my V dash. Okay. So that is what. So if you didn't understand this mathematical denotation also, it's fine. But understand this. So you have to pick few vertices such that each and every edge is covered. And also that should be the smallest subset. I have to pick the smallest subset. Again, here also I can pick all the vertices if I require. I can pick A, B, C, D, E, F, G, D, F, G. Okay. So I can pick all the vertices and call it as a vertex cover because all the edges are covered. but I have to pick the smallest of it. So that is the key. That is kind of puzzle. Okay. Again, it's a kind of puzzle. You have to pick few vertices such that should be the minimum number of vertices picked, and all the edges are covered. So can you try?
Sir, I can't able to digest it perfectly.
Okay. Okay. So what you
Yeah,
have to
sir.
do is
Actually,
hmm, hmm.
sir is trying to tell that we have to find out the vertices where from there we can reach to the all vertices minimally, right, sir?
It's not minimally. Okay. So you have to give me one vertex set, okay, one subset, such that if I pick any edge, if I pick DF edge, so at least D or F should be in my V dash. That's it. Like this, if I pick FG, at least F or G should be in my V dash. Okay. Before that, has everyone understood what is this covering means? So a vertex covering an edge. So understand that first. So a vertex covering edge means that vertex should be one of the endpoints of that edge. So if I take vertex A, this vertex A covers edge AC, edge AD, edge AB. So these are the three edges that are covered by this vertex A. Similarly, if I pick vertex G, okay, this vertex G covers these two edges. Okay, like this. So same like coloring, you have to pick the minimum number of vertices such that all the edges are covered. Okay, just now I gave example. If I have picked A and G, so the edges that are covered are this, and this. Still I have to cover this edge, this, and this. So in order to cover,
So E. So E will
Yeah.
cover EC, ED,
Ah,
EE, EF.
so if you have picked D, so this will cover CE, ED, EF, EB. Still I have to cover BF and FD.
F.
So I can pick F. Okay.
Now I am
So
able to understand, sir.
so now this will cover all the edges. Now if you take A, G, E, F as your vertex cover, you pick any edge in your graph. Thus that edge will have at least one of the vertices in this particular set.
Okay.
Got it? And this should be the minimum one. So if I have got something like 3 vertices itself, so if I can cover all the vertices using 3 vertices only, then that will be the minimum vertex cover. So see, difference between vertex cover and minimum vertex cover is that thing. So this is also a vertex cover. This is also a vertex cover, but this has the fewer number of vertices than this. So that is why this will be the minimum vertex cover. So the trick or the best method to follow while computing this vertex cover is you start taking the vertex which has more number of edges attached to it. So can you tell me which vertex has more number of edges? That is
E, sir.
E and F.
E, sir.
E, F.
And F.
E,
D
F, and
also.
D also.
D also.
Yes.
So start picking from any one of it. So you can pick E or F or D. Okay. So you start picking any of it. Any of it will give you. Let's pick E. So once I pick E, this is covered. This is covered. This is covered, and this is covered. So now I can pick D, F, anything. You pick D now. Also look at these things. This edge is left. So at least C or A should be in our vertex set. Okay. For this particular edge, C or A must be in my vertex set. So if I have chosen D, if I have chosen D, then this is covered, this will be covered, this will be covered. Now you see this edge is remained. I have to pick again F or G. So I will pick F. This and this will be covered. Now I have to cover CA and AB. So I have to pick A. So few people will, so if you have gone wrong, so this is where you can go wrong. Instead of D, just instead of D, I have picked C. Okay. So instead of D, I have picked C. So then what happens? This will be covered. This is not covered yet. This is not covered. This is not covered. This is not covered. Okay.
E is covering us, sir.
E will be covered. Okay. So this is covered. So now I have picked C. Now again, you see, I have to take A or B at least because this edge need to be covered. A or D because this edge need to be covered. Okay, I will start picking A. So I pick DA. So again, you see here. So once I pick A, I have to cover BF, FG, and DG. So in order to cover B and F, I will pick F. So this will cover this and this. So again, DG edge need to be covered.
Remains.
So I have to pick again G or D. Okay, now if you see here, I got 5 vertices in my vertex cover. And you might think that this is correct because I haven't missed anything in between. I have gone through some alphabetical order or some manner. But the thing is, unnecessarily we are picking C because C covers only one edge. Okay, so the trick lies here. So you start picking the vertices which has more number of edges connected to it. And once you pick that vertex, just remove all the edges that are covered. So just look at those edges that need to be covered. And in the next step, what you have to do is you have to pick a vertex such that more number of uncovered edges that are present to that vertex. So here, if I pick E, then the next one will be D or F you should choose, or A, not like C or G or B. So it has less number of uncovered edges to those vertices. So understood? So this is how you have to start. You start with a vertex which has more number of edges that are connected to it. Then you follow the same trend by adding vertex by vertex. So you will eventually reach to the minimum vertex cover. And in our course, we will not go beyond 9 or 10 vertices. So it is easy to find.
Could I ask something in this? You already said 9 edges, 9 vertices at most. Sir, there were 3 points like F, D, and E, which were covering the maximum number of edges per vertex. That was 4. Sir, could there be a situation in which amongst these 3, the choice we make could influence the future choices, if I select a particular vertex out of 3, I'm talking about hypothetical situation, not this particular one. Like I have 3 vertices to choose from. They all 3 of them are covering the same number of maximum and the same number of edges. But if I choose any one particular of them, and the future choices is influenced by the choice I make, the number of vertices in the minimum, the cover, maybe maximum or maybe more or less depending upon the choice I make.
Surely it will depend and it will affect. So if you know this a little extension of this graph theory, if you know optimization thing, so this particular finding the minimum vertex cover cannot be done in a given time. Okay, so it's not like 9 vertices or 8 vertices, we can do it. But if I have given you some 100 vertices graph, and if I ask you to find the minimum number of the minimum vertex cover for that graph within a given time, even computer cannot find it that easily. This is an non NP problem, so we call it as non polynomial problem. Okay, it's like you cannot find within a given time, you cannot find this is the minimum vertex cover. So for smaller graphs until 9 or 10 or maybe 20 vertices, we can manually do it, and we can check for each and start with each and every vertex, and we can find all the vertex covers and pick the minimum out of it. But when we have a large number of vertices, maybe 100 or 200 or maybe even large, then it is very difficult, or it cannot be find that easily. Minimum vertex cover is an NP problem, we say non-polynomial time problem. So it's like within a given time you cannot find it. Okay.
So vertex cover, you mean to say we need to cover all the edges
Edges.
that are connected to the minimum number of edges. So it's like a train junction. So so it's a like minimum number of junction. Like vertex will be the junction which will cover all the edges.
Yeah. So for answer for your question is, yeah, sometimes there might be cases choosing which vertex need to be chosen matters. Okay. So that is why you have to cross check it by taking few other options also. So for these graphs, you have to cross check for starting from E, starting from D, and starting from F also. But most of the cases you will eventually reach the correct answer. Once if you, we will not be giving such hypothetical cases graphs.
Okay, thank you, sir.
Okay.
Okay, sir.
And this minimum vertex cover is also not unique if you observe. Okay, it is not always unique. So here we have got A, G, E, F. So I can give you one more minimum vertex cover, which is D, DF, DFEA. Okay, so DFEA is also a minimum vertex cover. AGEF is also a minimum vertex cover. So likewise, you might get some other set which may also contain only 4 vertices. That will also be a minimum vertex cover. This is not unique. Okay.
So the number of elements will be this. I mean, the number of elements will be the same, but the elements might change.
The number of elements will be same, but the vertices may not be same. Okay. So the cardinality will be unique. So cardinality of this minimum vertex cover will be unique, will be 4 for this graph. Okay, but the vertices which we choose might be different. That's it. Okay. That is about minimum vertex cover. And next is maximum independent set. So maximum independent set is complement to minimum vertex cover. So in that way you can see. And so very one good property you can see is, so let's say V dash maybe the, okay, vertex cover, cardinality of vertex cover plus cardinality of maximum independent set vertices will give you the cardinality of total number of vertices. Okay, so maximum, what is this maximum independent set is? You have to find the largest subset. Again, it is related to vertices only. You have to find the largest subset now. So we are interested to look at maximum independent set and minimum vertex cover, because these are the optimal cases. So for vertex cover, we need to have the minimum possibility. For independent set, we need to have the maximum. We will try to find the maximum number of vertices which has this independence to each other. So what is this means is, what we have to do is we have to find the largest subset of V such that no two vertices in V are connected by an edge. So sorry, V dash. Okay. First of all, what is this independence means is, if there is no edge between two vertices, then those two vertices are independent to each other. Okay. So you see here A and E. So A and E doesn't have a direct edge between them. So therefore A is independent of E. So like this. So A and E are independent vertices. So like this, what I have to do, I have to pick these kind of vertices such that once I pick those vertices, then if I look at if I pick any two vertices from that particular set, they shouldn't have an edge connected to it. So it's like an independent to each other case. So if I pick, so in my independent set, if I pick some vertices, so let's say V1,
A, E,
V2,
F, A, E, F, G.
C and
okay.
G.
Okay. So if I pick V1, V2, V3 as my vertices in my independent set, then if I pick any two, so like V1, V2, so this should not belong to my edge set. There should not be any direct edge connecting V1 to V2, V1 to V3, V1 to V4, and again V2 to V3, V2 to V4, V3 to V4. So there should not be any edge between any two vertices in this independent set. Okay, and I have to maximize this. Okay, so let's see how to do this. So let me pick vertex C. So let us build even minimum vertex cover or maximum independent set, these all need to be built with one by one vertex. Okay, so let us build the independent set, maximum, sorry, independent set. We will try for independent set. Let us analyze whether it will be maximum or not. So let us start by picking C, vertex C. So once I pick vertex C into my independent set, I cannot pick A and E because they are sharing an edge. So I can pick B, D, F, G, anything. So I will pick B. So once I pick B, I cannot pick F. And once I pick, so I can pick D or G. So I can pick D. Okay. So this is one independent set. So what I have picked this, this, and this. And I cannot add any of the vertices A, E, F, G to this set because it fails the property of no two vertices in V dash are connected. Okay, let us call Vi. So no two vertices in Vi are connected by an edge. This property will be failed. So if I add any other vertex like A, E, F, G into this set, then this property will be failed. So therefore, this is the independent set we got. And we have to check whether this is the maximum or not. So how do we check that? So what is the best way to check?
We have to start which have lower number of edges or connections.
Okay. Okay, you can do that, but that is also not that very effective. But the most effective thing is try to find the minimum vertex cover and take the complement of it. So if you know how to find the minimum vertex cover, find the minimum vertex cover and take the take the vertices which are not in that vertex cover. So here if you see AGEF is the vertex cover. Okay, so vertex cover is AGEF. So the independent set will be, we shouldn't consider AGEF, so C B
BD.
B. Okay,
Yeah.
we got the same thing. Okay, so this will be an independent set. Again, you have DFEA as a vertex cover. So if the vertex cover you have chosen is DFEA, then the corresponding independent set, maximum independent set will be
BC.
BCG. Yeah, you can check BCG. So these three are independent to each other, and this will be the maximum independent set, and this will be the minimum vertex cover. And if you see the cardinality of VC plus cardinality of VI, it will be the cardinality of vertices. Okay, this is true for any graph. For any given graph, this is true.
Sir, can you
Okay.
write that cardinality part?
Right?
The cardinality part. So we
In
can
a
take
separate
a
line, is
snapshot.
it?
Yeah. We can take a snapshot.
Okay. Anyway, I will upload this.
Where, sir? Portal?
Portal.
It would be helpful.
So the cardinality of VC plus the cardinality of VI. So you have to understand VC and VI will be equal to the cardinality V. So in expressions it will be VC plus VI will be equal to, okay, where VC is vertex cover, VC is minimum vertex cover, VI is maximum independent set, and V is the set of vertices in the graph. Okay, so this is an important connection between maximum independent set and vertex cover. If you know one thing, the other thing you can deduce directly. Okay.
Sir, one small
Excuse
doubt
me,
is
can you
this.
show the formula on it?
Sir, I have small doubt. In definition, you have mentioned VC or VI is subset of V, right, sir?
VI is subset of V.
So why the equal sign is there? Equal sign is just to show that it can be the entire subset of entire the element of the V also, is it?
See, I can give you an example. So if there are no edges at all, so V1, V2, V3, this is also a graph with 4 vertices with
Out
no
to the
edges. Okay. So now if I compute the independent set, my independent set will be V1 whole vertex set.
Yes.
Correct. So
So
each and every vertex is
is this a
independent.
graph, sir? Is this a graph without edges?
Yeah, this is a graph.
Okay.
So this is a graph with 4 vertices and 0 edges.
Okay. So, but we don't have any information from this graph, right, sir?
Isolated graphs, isolated places.
Okay, we can't get any information from this graph. Like usually we give to example of train, airline route, something. So there is no meaning of this graph, right? So, as I can say,
there is meaning, right? See, if there is, so usually you can take 4 vertices. They are connected. Okay, completely connected. Okay. So you see here, I can go from here to here, go from here to here. This edge represents I can go. Okay. If your edge is representing, draw an edge between 2 vertices such that you cannot reach from one vertex to another vertex. So how will you draw and how will you show? So your edge is now your edge is representing those vertices. Okay, those cities are not connected by a road.
Mhm.
So if every city is connected by road, every city is connected to other city by road, so there are no edges to draw at all.
Okay, is that we can find out? We can just configure this. We can just conclude this. I mean, say that.
So if there
Okay.
is a no edge, then obviously it refers that there is no road, there is no cities that are not connected to each other. That means all the cities are connected to each other. So the way which we define the edges matters. Okay, sometimes we may define like this or define like that. Okay.
Okay.
Sir, is there any mathematical tool so that we can find minimum vertex cover rather than
No,
going
no,
through vertex one by one?
that is what I said earlier. This is not. There is no algorithm or anything to find minimum vertex cover.
We
Okay.
have to go
So for
through manually and answer may be
so
differ.
for smaller graphs we have to go manually. For larger graphs it is non-polynomial time problem. Okay. So it is not able to be solved within a given time.
Okay,
Sir, in
and sir,
this
answer may
example,
differ among two students, right? Answer may differ among two students if different
Answer
students.
may, so that is
Answer
what
may
we
differ,
can
no?
have. See, the
Yeah.
vertex cover may be different. The number of the sorry, the vertices which you choose may be different, but the
But the
cardinality
number
should
should
be
be
same.
same. Okay,
The
now I
number
got
will
it,
be.
sir.
so in this example where we don't have any edges, vertex cover is 0, right, sir?
Vertex cover is 5, right? There is
Okay.
you no need to pick any vertex. All the edges are covered. There are no edges. There is no covering at all. No need to cover any edge. Right?
Okay.
If there is
So,
one edge, if there is an edge like this, then I have to cover this edge. Then only that covering comes, right? If
okay.
there is no edge at all, what will you cover?
So vertex cover,
Zero.
the subset of that vertex cover, I mean, so the vertex cover set will be 0, right, sir? Cardinality will be
Not
0.
zero.
5 small
Cardinality will be 0. Vertex cover will be 5.
5.
It's a set.
Okay, set is, yeah.
Null set.
Null set. Again, this is Vi. Okay.
Okay.
Yeah. Okay. Let's move then. Let's move and look at into this matchings. So previously, whatever we have seen, vertex cover, graph coloring, vertex cover, maximum independent set, all are related to vertices. But this matching is related to edges. So now we are looking at edges and we are trying to pick few edges from the edge set. And how we pick those and what is this, we will see now. So what we have to do is we have to find a maximal subset of edges. So how many of you know the difference between maximum and maximal? Is there any difference first of all?
Yes, sir.
If yes, what is the difference?
So is maximum a point and maximal a function or something?
No. Okay, first of all, let me clear this. Maximum and maximal both are different. Okay, maximum subset refers to something. Maximal subset refers to something.
In lectures are told, I'm not remembering. Yeah.
Okay. So we will discuss that also. Let us first understand what is this definition. So what is this matching means is you have to find a subset. First of all, remove that maximal and maximum side. What we have to do is we have to find a subset of edges now, not the vertices. We have to find the subset of edges such that all the edges in E dash. So let us say E dash is the subset such that all the edges in E dash are disjoint. So disjoint here means they don't share a common vertex. So let me write it. Disjoint means don't share a common vertex. So if you see in this particular graph, AB edge and BC edge shares a common vertex B. So that means this edge AB and edge BC are not disjoint. Okay. And AB and ED, if you see AB and ED, they are not sharing a common edge. So AB edge has A and B as the vertices, and ED edge has E and D as the vertices. So there is no common edge. So that means AB edge and ED edge are disjoint to each other. So that is what disjointness means. And what I have to do, I have to find a subset such that I have to pick few edges from the graph, and those edges need to be disjoint. So all the edges need to be disjoint. Whatever edge I pick, all of them need to be disjoint to each other. Okay. And what I am doing, I am trying to get the maximal. So maximal means if I add one more element to it, then it fails the condition. Okay. So once if I find a subset, and if I say it is the maximal subset, need not to be the maximum. So sometimes it may not be the maximum, but if I try to add one more element or one more edge into it, here in this context it is edge. If I add one more edge, it fails the given condition. The condition is all the edges in E dash are disjoint. This is the condition. So we try to find the subset which need to be the maximal enough. Maximal enough means if I have chosen some three edges, and I can get maximum subset which is 4 edges, such that all the 4 edges are disjoint also, it's fine. Even though if I get 3 edges and all these 3 edges are disjoint to each other, and if I add one more edge to this disjoint, one more edge to this set, then the property will fail. So let us analyze it by an example. So what is this maximal and maximum? So let me pick AB.
So,
Okay.
so the cardinality of the set will be same all the time?
No, may not be. So that is, we will see. See, let me pick AB. Okay, vertex C, sorry, edge AB into my E dash. Okay, so I have picked AB edge. So once I pick AB edge, I cannot pick AF, BF, BE, BC, right? Because all these edges will share a common vertex. So then I have to choose either CE or DE. Correct. Let me pick CE. Okay. So once I picked CE, I cannot pick D anymore. So now see, E dash has only 2 edges, 2 disjoint edges. If I try to add one more edge into this E dash, what will happen?
Won't be
They will
disjoint.
not
It will
compare.
have common vertex.
It will not satisfy this condition that E dash, all the edges which are in E dash are disjoint. So this property will be failed. So I cannot add any edge to it. So this will be a matching. So this is a matching. Okay. And this is called maximal matching. So it's not maximum. I will show you. I will give you the maximum matching for this also. This is called as the maximal matching. So that's it. I can add only 2 edges to this. I cannot add any edge to this particular set. because if I try to add one more edge to this set, the disjointness will fail. So this is the maximum number of edges I can have in this particular E dash. So now see, I will choose AF, BE, sorry, BC and ED. So can I choose this? AF,
This will satisfy the condition.
BC, DE. Even though if I choose these three edges are disjoint to each other. Observe,
Right.
this AF is disjoint to BC and these two edges are disjoint to ED. Okay, now what I got three edges that satisfy this condition. Correct?
Yes, sir.
Previously I got only two, and those two will satisfy the given condition also. That is also a matching, kind of matching. Okay, this is called maximal matching and this is called maximum matching. So maximum I can have only three edges possible.
Without failing this condition,
Without failing this condition. So I can have only maximum of three edges only. I cannot have some other set which has four edges. Okay. So I can have a maximum of three edges in my set. So that is called maximum matching. And this maximal matching is, there are only two edges into this, but it will not allow any other edge at all. So that will fail the condition. So that is called as the maximum. It may not be the maximum, but the properties are satisfied, and with that particular set I cannot add more elements into that set such that the condition will retain.
Okay,
that
so
is the
because of
difference between
selection of the edges in such a way that we can't add any one of that.
Right. So that is the difference between
Is there any
maximal.
possibility that we can add in maximum case, sir? Is there any possibility that we can add any edge in case of maximum?
No. See, if there is possibility, then this will not be the maximum.
This will not be the maximum.
Okay.
Okay, so we have to select the vertices in that order, in that manner.
So this maximum matching is also a maximal matching. Okay, so maximal matching, because I cannot add any other edge to this. This is the maximum number of edges that will be in this E dash. Okay, so if I add one more element to it, it will fail the condition, given condition. So this will be maximal matching also. This is the maximum matching also, and this is also called perfect matching. So what is this perfect matching is? So the matching covers, all the vertices. So you see this edge covers AF vertices, this edge covers BC vertices, this edge covers ED vertices. So all the vertices are covered by these three edges. So therefore that is called as a perfect matching. Perfect. So that means each and every vertex is included.
So is this condition, sir, of a maximum we should cover the all edges, all vertices?
No. Sometimes it may not cover. So I will just add. If I add an edge here, D, E, F, G. So now you see G vertex will not be covered. Whatever combination you pick, you might have picked AF, BE, and DG. Then C will be remained.
So in this case, if we add with the blue E dash, if we add DG, then that will cover all the vertices.
No, then E will not be covered, right?
D is there already.
But there is CE already there.
No, okay, see, if C is there,
That blue E dash I'm talking about.
okay, blue E dash, then F is not covered, right?
Okay, yes, sir.
See, it is very easy to understand if there are odd number of vertices. Okay, so pairing, how will the pairing happens between two vertices? If I pick an edge, then two vertices are covered. So like this, I have to pick. Yes or no?
Yes, sir.
See, if I pick an edge, then two vertices are covered. A, B. CE is covered. DG is covered. So for these three edges, 6 vertices are covered. But I have 7 vertices in my graph. So at least one will be remain. So that is why a graph, this is also one more properties. There are numerous number of properties. For a perfect matching, the graph should have even number of vertices at least. First condition is that the graph must contain even number of vertices. Then only the perfect matching might be possible. Okay. If there are odd number of vertices in your graph, then sure shot you can tell that there is no matching that is perfect, or there is no perfect matching possible. Okay, so that is one more condition you can see.
So
There
can
are
I
many
write down,
many.
sir? So are you saying that perfect matching would be having the even numbers of edges?
No, not the edges.
I mean, say that.
If the graph has even number of vertices, then only perfect matching may be possible. It's not must
Okay.
also. Okay, it is also may be possible.
Okay.
Hmm?
So, sir, maximal matching is some kind of subset of maximum matching, is it?
No,
Like
no,
not
it's
subset
not the subset.
exactly, not subset actually, but it will be minimum. It will be less than the maximum, right?
It will be less than the maximum matching. But
No.
if I try to add one more edge, it will fail the condition. Okay.
Okay.
So that is how it is. And yeah, there are many properties you can actually deduce.
Sir, before moving ahead, can you conclude the core difference between maximum and a maximal once again in short form?
Okay. So the maximum matching contains the cardinality of the maximum matching will be the largest. Okay. So you cannot have a matching which has more number of edges than the maximum matching. So the maximum matching has the more number of edges inside it. But for the maximal matching, it may not be the case. It may not be the maximum. For maximal matching, what happens is, even though you have only 2 edges, if you try to add one more edge, that will fail the given condition. That will not be the maximum, that will be the maximal.
So there could be conditions where maximal both can be same.
Both can be same. See, maximum matching is a maximal matching. Okay.
Okay, now I got it, sir. Now I got it. Yeah.
Maximum matching is a maximal matching, but maximal matchings may not be the maximum matching. It may have less number of edges inside it.
Yes, sir. There must be some other arrangement we can get maximum, but yeah.
You
Now
can
I got
get
it,
the
sir.
maximum. Yeah.
So sir, here, here blue E dash or red E dash both are acceptable, sir.
Both are maximal matchings. We are trying to find maximal only. If maximum is asked, then only you have to look for maximum. But instead, we will try to look for maximal only. We will try to pick few edges. We will start picking edges, and we will try to accommodate more number of disjoint edges into the set.
It's like something kind of local maxima and global.
So maximal is greater than equal to maximum. Is it right?
Maximal is less than or equal to maximum. Maximal elements in maximal will be lesser or equal to maximum.
Yes. I said it opposite. Okay, clear, sir. Thank you.
So this maximum which we are comparing with maximal is this maximum independent set?
No, this is not maximum independent set.
Which we are comparing with the maximal matching. This maximum which we have written next to the maximal, this maximum, is it the maximum independent cover?
It's not the maximum independent problem. It's for, see, maximum independent set is for vertices. Okay. So are you trying to ask me that whatever the maximum refers to maximum independent set is the same referring here?
Yes, sir. Actually, I'm trying to clarify what this maximum means. I understood the maximal part.
Okay, maximum means that thing only. Like whatever is there for independent set, maximum independent set, that is the maximum here. So maximum definition is maximum. Whatever the definition we have for maximum is the same maximum here also.
Okay, thank you, sir.
Okay, let's move ahead. And we will discuss what is this degree. Degree is also very easy topic only. So degree of a vertex is defined for undirected graph separately and directed graph separately. So degree, when we say degree, it refers to an undirected graph. Okay, we will discuss what we will refer to degree in directed graph. But when I say degree of a vertex, if I didn't include any pre words to degree, then the degree is referring to an undirected graph. And what is this degree means is the number of edges that are connected or incident to the vertex I. So the degree of a vertex I in an undirected graph. So in an undirected graph is the number of edges that are incident to vertex I. Okay. So you have to count the number of edges that are incident or connected to that vertex. That's it. So that is the degree of the vertex. So look at here. Let us try to compute for E. So let me take an example. So if I look at vertex E, okay. So once I look at the vertex E, so how many number of edges that are connected to vertex E?
3.
What D? C and B.
3, sir.
1, 2, 3. So the degree of vertex E is 3. That's it. So you have to count the number of edges that are connected to that vertex. We will call, see, these are called the terms incident. So incident means it is between edge and vertex. So if they are connected, they are called incident. Okay. And adjacency is between vertices. So understand these terms, just go through the lectures again. So be used to these terms. So let us try to find the degree of F then. So what is the degree of F?
3. Sorry, 2.
2, sir.
2. So there are 2 edges that are connected or incident to F. So I will use incident from now onwards. So what is the degree of B?
3.
4.
4.
3, sir. 4, 4, 4, 4.
3 plus
1,
1.
2, 3, 4. Okay. A. For A?
2.
2. C?
2.
2.
D is 1.
D1.
Now, again, there are few properties of this degree. So just add all the degrees of all the vertices. What we will get? So 1 plus 2 plus 2 plus 2 plus 3 plus 4. So we are going to get 14. And how many number of edges are there in the graph?
7.
So you count 1, 2, 3, 4, 5, 6, 7. So the cardinality of edge set is 7. And the sum of please be on mute. Okay. So the sum of degrees of all the vertices is 14. So there is a beautiful property or a beautiful theorem called handshaking lemma. So which says sum of degrees of all vertices will be equal to twice the number of edges. Okay, there is a connection between the number of edges and the total sum of degrees of all the vertices. So you pick any random graph, undirected graph. This is only, we are only dealing with undirected graph till now. So when I say degree, that is referring to an undirected graph. Okay. And this property will hold for all the undirected graph. There is no exception.
Only
Because
for undirected.
only for undirected. So it's very easy to understand also. So this particular edge, you see, this particular edge will constitute 1 degree to B and 1 degree to C. So one edge will give
Right.
1 degrees to each of the attached vertices. So like this, every edge. So this edge will give 1 degree to F and 1 degree to B. So like this. So each and every edge will give 2 degrees. Therefore, if I add all the degrees, I will get 2 times the number of edges. Okay, this is the degree. Degree is very simple. You have to count the number of edges that are incident to vertex, that particular vertex. And degree is referred to a vertex in a graph. Okay, there is no degree of a graph. Okay, don't be like that. So degrees are always computed to each and every vertex.
Sir,
And
undirected
what
means
happens?
we can go both ways, right?
We can go both ways. Undirected or bidirectedness. Both are same.
Both are same. Okay.
What if?
So what do you mean by adjacency? You said some adjacency incident.
Adjacency means between two vertices. Okay. So I will say vertex A is adjacent to vertex B. So when will I say they are adjacent is if they share a common edge, direct edge. So like this, if there is an edge between two vertices, then I will say neighbor. So adjacency means neighbor. Okay. So vertex A is adjacent to vertex B. Okay. Between two vertices, we will use adjacent. And between edge and vertex, we will use incident. So this edge is incident to vertex A and this edge is incident to vertex B. Okay. So incidence or incident is used between edge and vertex. Adjacency is used between two vertices. Okay.
Thank you.
Yeah. So now let us look at the directed graph case. So what if the graph is directed and what we will call? So we will not be calling a degree of a vertex, and in directed graph, each vertex will have two things. One is in degree and another thing is out degree. Okay. So there are two things now, not a single degree. We will have two degrees, which is in degree and out degree separately. So what is this in degree means is number of edges that are
coming into that vertex.
Towards
yeah towards the vertex,
towards I or towards the vertex I. And what is this out degree means number of edges
going out of the vertex
that are going out from I. Okay. So number of edges, here also the number of edges, but in a directed graph, each vertex will have some edges coming towards that vertex and some edges going away from that vertex. Okay. For example, see here. So let us, I will try to compute for 2 and I will ask you to compute for others. So let us try to compute for F. So blue color, I will denote it for in degree, and red I will give for out. Okay, out degree. So let us see for F. So for F, what will be the in degree? So what you have to do is the number of edges that are coming towards I. So how many edges that are coming towards I? Sorry, towards F?
3.
2.
Two. Sir, from B to F, it's not directed.
Is
So
coming
it's
to
2.
F.
So see, in a directed graph, if there is no direction given to any of the edge, treat it like it's a bidirectional.
Bidirection, yes.
Okay, bidirection.
Okay, then it's 3.
So it's a bidirectional. So you feel that. Then now see how many inward coming edges are there?
Three.
For F, 3.
3.
Now, how many edges that are going out from F?
F1.
2.
Sorry, 2.
2, sir.
Just one, sir.
One.
I mean 2.
2. 2.
One
Two,
or
sir,
two?
two.
Two.
2,
See,
2,
F,
B and
F2E
B.
and F2B.
F2E and F2B. So you have to be very careful in directed graphs cases. Okay, so 2. So 2 is the out degree for F, 3 is the in. So the out degree of F is 2. Similarly, in degrees of F is 3. So now tell me, what is the in degree for B?
2.
So how many
2.
edges that
2,
are
sir.
coming towards B?
2.
2.
2.
2.
And what is the out degree of B?
2.
2.
4.
3.
3, sir.
4. 4.
Yeah.
4.
4.
3, sir.
4.
4.
3, 4, 4. Yeah, 4. B2A is there also. Yeah, 4.
4.
So B2F is also there. You have to see. So outward B2A, B2F, B2E, B2C. So 4. So like this. So let us compute in degrees for all the vertices then. What will be the in degree for C?
2.
2.
2.
2, sir.
In degree for D?
0.
It is,
0.
there is no in degree,
0.
sir. 0.
There are no edges that are coming towards D. So what is the in degree for A?
Yeah.
3.
1.
A.
1.
Sir, 4.
1. 1.
Oh, A. Sorry, A is
For
1.
A. And E?
Oh, so
Three.
sorry, sir. I heard
3.
E. E is 4, sir.
3.
3.
4E,
3
3.
on,
Oh, sorry.
3
1,
only,
2,
right?
3. Yeah, 3, 3, 3. Yeah, 3.
3.
Yeah.
Now out degrees also. So number of edges that are going from C?
0.
0.
Outward, 0.
0.
And for D?
1.
1.
1.
For E?
2.
2.
2. This
E
EF
2.
and EC. 2.
2.
What is for A?
1.
2.
2.
2.
2. 2.
2.
2, right?
2.
2, sir.
2.
Hmm.
So don't get confused. So take some time and
Hmm.
just be sure that your answer is correct. Okay. So this is how we can compute in degrees and out degrees for a directed graph. And the most important thing is, so I'm saying it most important. Never ever say that
Okay, plus. Okay. Okay.
okay.
Hmm.
So degree of a vertex is equal to in degree plus out degree. This is the big blunder in graph theory. Okay.
Hmm.
So there is no, that is what I said, there is no term called degree in a directed graph. Okay. So if it is a directed graph, there are in degrees and out degrees. If it is an undirected graph, then there is a degree.
Right.
Okay. And I am again saying this, please note, see, even though I stress this much, most of you will give wrong answers in exam. So degree will not be equal to in degree plus out degree. Okay, there is no degree at all in a directed graph. Okay. So okay, it's already 10. Shall we continue or?
Sir, I have a small doubt with the exam related doubt. Is it, sir, exam is going to be computer based or written, sir?
Computer based only.
Computer based. Okay, so just wanted to verify because I had that small doubt. Previous exams were computer based only. So, okay, sir.
All exams will be computer based.
Computer based only. Okay. So what shall we do? Shall we ask the other instructor to take the remaining topics tomorrow?
So tomorrow there is
Yes,
a
yes.
solve with us session.
Yeah, solve with us only. I
And
understand,
we
but
have completed only 20% yet.
See, we have adjacency matrix, adjacency list, and DFS, DFS.
DFS, yeah.
Tomorrow?
those are very important topic.
Yeah, these are very important, I know. Okay, let me do one thing. Adjacency matrix and adjacency list I will complete today. DFS and DFS, I will ask the other instructor to do it tomorrow and then take the solve with us. I don't think solve with us will take that much time. And also in solve with us slides also you have pretty decent stuff like topological sorting and everything. So you can do topological sorting while solve with us is going on. I will ask BFS and DFS to be dealt tomorrow. Just give me some 15 minutes more. We will try to finish this as soon as possible.
Okay, sir.
Okay.
Yes.
Okay. Let us now see what is an adjacency matrix is. So adjacency matrix is another way to represent a graph. And can anyone quickly give me what is the most important? So why already we have a graph, and as it is a pictorial representation, it is very easy to understand. Then what is the use of this adjacency matrix? Why we need to represent this graph in another way?
So sometimes it's very difficult to find out minimum root and all something. So that's why adjacent matrix will give you more clear picture.
Okay, maybe.
And we get a procedure, sir. Procedure to solve the problem. The computer cannot understand the graph images, but this matrices can be solved using the computer and mathematically also.
Perfect. So that is the main reason. Computer, see, whatever we are doing now, it should be understandable to computer, right? So you give a an understandable graph. See, if you give this graph to computer, it is very hard to read it, or the machine will take a lot of time to understand, or it will not understand at all. It will give you some errors. So in order, how will you let the machine know what type of graph you are referring to? So for that, this particular adjacency matrix is very helpful, because you can give the matrix representation to the machine. Machine understands the matrix form. Correct? In codes or codings also, you know how to give the matrix, right? Array. In array format we will give.
Nested dictionary.
So in that, if you give in that manner, it will understand, oh, see this, there are some 6 vertices and there are some edges connected to between the vertices, and it will perform the required, whether you are asking for coloring or anything, it will give you the output. So okay, so what is this adjacency matrix is? It is actually a table, or actually we call it as a matrix also, both ways, table or matrix, that contains some rows and columns, and each row represents a vertex, and also each column also represents a vertex, and each entry in the table, so whatever the entry we are going to give in that matrix, will be either 0 or 1. And those entries will be dependent. If there is an edge between two vertices, then the corresponding row and then the corresponding entry will be given as 1 or else 0. So for example, here you see there is an edge between A and B. So there is an edge between from A to B, there is an edge. From B to A, there is an edge. So now you see from A to B, there is an edge. So row A and column B, the entry should be 1. So this 1 represents there is an edge from A to B. And here also there is an edge from B to A also. It's an undirected graph. So from B to A also there is an edge. So here also we will give 1.
Diagonally they will be symmetric.
So again, there are no loops. Loops means the same vertex having an edge to it, connected like this. So we are dealing with simple graphs here. Yeah, self loop. There are no self loops. So from A to A there is no edge. So we'll give 0. If there is an edge, we will give 1. The entry value will be 1. If there is no edge, the entry value will be 0. So like this you have to fill. So now you see, let's start from vertex A. So from A to A, there is no edge. From A to B, there is an edge. From A to C, there is no edge. Direct edge. This refers to direct edge only. So from A to C, there is no direct edge. It will be 0. From A to D, there is no edge. 0. A to E, no edge. 0. A to F, there is an edge. So the entry will be 1. Like this, we will fill. Next, we will go to vertex B. So from vertex B, there is an edge to A. There is an edge to C. There is an edge to E. There is an edge to F. And there is no edge to D. And there is no self loop. 0. So like this. C to A, there is no edge. So like this, we can fill. C to B, there is an edge. C to C, there is no edge. C to D, there is no edge. C to E, there is an edge. C to F, there is no edge. So like this, we can fill. D to A, no edge. So I will fill. Just let me know if you didn't understand. Okay. So E.
0.
Okay. So this is how the adjacency matrix is represented. So both are same. So this is for our understanding and this is for machine understanding. So both, so if I give you a graph, you can be able to compute the adjacency matrix. If I have given you the adjacency matrix, then you can be able to draw the graph. Okay. So vice versa. So if I have given this adjacency matrix, so you just draw, by looking the adjacency matrix, you see the number of rows or the number of columns will give you the number of vertices. And if you see the entries, so if there is an one entry here, so that means there is an edge from A to B. So draw an edge. So like this, you can build the graph by looking into the adjacency matrix. And also for an undirected graph, if you see along this diagonal, so this is called the diagonal. So along this diagonal, the matrix will be symmetric. So symmetric. So whatever the values are here, if I flip this along this line, so if I rotate this along this line, I will get the same matrix. So
Or
you
we
see
can
this
say it's a transpose also, not a transpose. Same.
transpose. If people understand what is a transpose, it's okay, well and good. So the transpose will be same. This transpose means this thing. So ij entry will be same as jith entry. Okay, ij means first row, maybe third column entry will be same as third row, first column entry. So you can check. So first row, third column is 0. Again, third row, first column is also 0. So like this, ijth entry. So ijth means ith row, jth column entry will be equal to the jth row, ith column entry for an undirected graph. Okay, that is what it. So for an undirected graph only this holds true. So by looking at the adjacency matrix itself, you can guess whether it is a directed graph or an undirected graph. Okay. And what else? Yeah, if you add the row values, what will you get? Can anyone guess?
Number of edges from A something.
What is it? What is it refers?
Vertex.
Vertex. Add the values.
Number of edges coming from row. If you're row wise counting, so number of edges coming from particular
For an
vertex.
undirected graph, tell me for an undirected graph what that means.
Oh, I'm not sure.
Degree of that particular vertex.
Yeah,
Correct.
that's degree.
So that is called degree of the vertex. So add the values of row I, you will get degree of the vertex I. So you can check this is 2, 4, 2, 1, 3 and 2. So these are the degrees of each and every vertices. Okay, that will give you for an undirected graph. For an undirected graph, if you add rows it will give you the degree. If you add columns also, it will give you the degree. Okay, if you add the columns also, it's fine. You will get the same. Okay, so whatever, which one you feel comfortable, you can add that. So it will give you the degree.
So for the transpose thing, only one line should be there. Like I am asking in layman terms, from top left to bottom right, we have drawn a line for the transpose check, right? My question is only, is there any possibility that we can get from bottom left to top right, or only one line
No,
should
no, 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 no.
that
That
is
is
right
not
to
called
left?
as a diagonal basically. So for a
From,
matrix, this is referred to be as a diagonal.
okay, from top left to bottom right is known as diagonal in matrix, right?
Principal.
Thank
Principal
you.
diagonal. Yeah. Okay. For a directed graph, the same approach. If there is an edge from vertex I to vertex j, I will give the entry value as 1. If not, it is 0.
What is the cardinality of the adjacency matrix?
Cardinality of the adjacency matrix. What do we mean by cardinality of?
Number of edges are 1 1. Number of counting 1 1, is it? No. Not sure.
So are you asking the number of non-zero entries in the matrix?
In the adjacency matrix, we will have x or the ijth value same as jith value. So is it addition of all the ij values divided by 2, or it is
No,
the
no.
I
See,
have not understood that cardinality part.
I didn't mention cardinality at all.
No,
See,
I was reading it over, so I just wanted to know that.
No. See, first of all, first point is cardinality only refers to sets. Okay, set. So if I have given a set, cardinality refers to the number of elements present in that particular set. Okay.
No, there was this cardinality of the matrix, which was asked, adjacency matrix.
No. Where it is asked?
I think it was in mathematics.
Yeah, in mathematics only. Okay, anyhow, just listen to me. Cardinality only refers to sets, not for any other things. Okay. Cardinality means the number of elements in a particular set.
In a particular set. Okay.
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 Now, when I say cardinality of an adjacency matrix, this doesn't make any sense. So, because adjacency matrix is not a set, first of all. So, just come back if you have read it somewhere, or just make sure what you have read first. So, if whatever you have read is correct, then just come back and let us know where it is given.
Okay.
Okay.
Okay, thank you.
Thanks. Okay. Yeah, for directed graph also, it's the same thing. So I will fill it. So from A to A, there is no edge. From A to B, there is an edge. So you see, from A to B, there is an edge. So 1, A to F, and from B to E, B to C, C to nothing, E to C, sorry, D to E, E to C, and F, E to F, and F to B.
F to E also, sir.
F to E. Okay, so these are the entries, others will be 0. So correct me if I am going wrong.
Guys, can you
We are only considering outgoing.
No, all are included, right? Oh, sorry.
So if it is,
Sorry. These are outgoing only. So see, from row to column. So you have to see edges from row to columns.
Okay.
So
Thank you.
from A to B. So if there is an edge from A to B, then I have to give 1 here. So you see here now there is 0 for row B and column A because there is no edge going from B to A. So this edge only coming from A to B.
Sir, can you mute
I
all for me?
request everyone to please be on mute. Okay. So that is why there is no edge from B to no edge from B to A. That is why this entry is 0. Row B column A entry is 0.
Yes, sir. Understood. Thank you, sir.
So now if I add all, so if I add all the values in row I, what will I get?
Out degree.
So in out degree, sir.
Out degree. Correct. Out degree of I. And if I add columns, what will I get?
In degree, sir.
All the column. Column I.
Yeah, in degree, sir, for column.
Correct. In degree of I. So from adjacency matrix also, you will get all the properties and all the this in degree, out degree and everything via adjacency matrix only. No need to draw the graph and check again. So this adjacency matrix is nothing but another way of representing our graph.
Sir, is the diagonal here in second matrix does represent anything or?
No, nothing. So this will fail. Now you see, if I look at the diagonal, it will not be symmetric about diagonal. That means ijth entry for few values, ijth entry will not be equal to the jth entry. So the best example is this. So row A column Bth entry is 1, but row B column Ath entry is 0. So they are not equal. So from here itself, you can say that it is not an undirected graph. It is a directed graph. Okay, if it is symmetric along this diagonal like this, then the corresponding graph is a undirected graph. If it is not symmetric, then it is a directed graph. Okay. And next is adjacency list. So what we do in this adjacency list is, this is also another way of representing graph. What this adjacency list is basically is, what we do is we draw the table like this, and we are going to list all the vertices that are neighbors of each vertex. Okay, neighbors is again, neighbors means adjacent. And again, there are two different types of adjacency lists here. So one is with respect to in degree, we say. So with respect to in degree, we count the neighbors. And another thing is with respect to out degree. So what we do is, sorry, with respect to inward edges, incoming edges.
Sudarshan Ramanathan, can you please mute yourself?
Yes, sir. I'm sorry, sir. Sorry.
Yeah, please. Okay. With respect to outward edges, outgoing edges, you can say. Okay. So incoming edges means, see, with respect to this FB. So FB is an incoming edge to B. Okay. So if it is an incoming edge to B, then I will say this F is a neighbor to B. Okay. So with respect to A, I have to look for what all the edges that are coming towards A, and I have to look for their corresponding vertex, the opposite vertex. So you see, for A, first of all, there are no incoming edges at all. So there will not be any incoming neighbors. So the set will be empty set like this. For B, if I look at, for B, there are three edges that are coming towards B. There are two incoming edges to B. So therefore, A and F are the incoming neighbors. You can treat it like that. So A and F are the neighbors to B with respect to incoming edges. So with respect to these incoming edges, A and F are neighbors to B. So therefore, in the Bth row, I will add this list containing this set containing A and F. Similarly for C. So for C,
B and E.
there are two edges coming towards C, and the two incoming neighbors are B and E. So B and E. And for D, there are no incoming edges. So again an empty set. For E, if you look at for E, BE, FE, DE.
BDF.
So the neighbors are B, D, F. And finally for F, AF,
A and E.
E. So A and E. So now you see, from this adjacency list itself, you can again draw the graph. So again, adjacency list or the graph, both are same. So it's another way of representing. Okay. And the main usage of this adjacency list is time complexity. It saves a lot of time. So if I have the adjacency matrix, you see, if I have the adjacency matrix, I have to go through each and every entry. So there are, if there are some 10 vertices, then in my adjacency matrix, there will be 10 square 100 entries. And I have to go through each and every entry and look for whether it is 0 or 1. So the time complexity is very, very large compared to adjacency list. So when I look at adjacency list, the time complexity will be very less compared to adjacency matrix.
Adjacency
So that is the
list should also exist for non-directed graph as well, right, sir?
It will exist, right? It's a bidirectional, so
Yeah,
it will
it's
have.
a bidirectional, so we can, yeah.
So see, why we study adjacency list is because this is the advantage of studying adjacency list. So the time complexity will be very less compared to adjacency matrix.
Got it.
Okay. Yeah. And again, with respect to outgoing edges, so you have now you have to look for outward edges. So now
BF.
for A, you see there are two outgoing edges. So that means for A, this B and F are the neighbors. So write it. B and F are the neighbors. For B, there are two
C and E.
outward C and D. For C, there are no outward going edges.
Null set.
Sorry. Null set. For D, it will be E. So there is one edge going outward. So E is a neighbor. And for E,
FC.
F and C. CF. And finally for F,
B.
there are
B and
B
E.
and E. See, both are adjacency lists, but the first list is basically with respect to incoming edges, and the second list is basically with regard to outward edges. So that's it. For today, we will take a break then. Just go back. I will just upload this PDF on the portal. Just sit for yourself, maybe in the tomorrow morning or whenever you got time. Just go back, watch the lectures, come back, watch today's session again, or else at least go through the PDF what we all discussed, and try to solve as many problems as possible, and try to enjoy this concept. So the more you enjoy, the more you will understand.
Sir, by when we can expect the PDF?
So I will forward it now. Maybe by tomorrow morning they will upload, I guess.
Where can we see in the portal, sir?
Maybe in the supplementary contents, I hope.
It will take more time than tomorrow morning.
Why?
You have mentioned a lot of time that it will be uploaded at tomorrow morning, but it never gets uploaded tomorrow morning. It will take at least 24 hours.
Acha.
Yeah, sir, it will take time. It would be great if you upload somewhere else and provide.
See, if I know, I will upload it directly now itself. But I don't know how to upload, right? I have to give to the portal team and they will upload. I will check.
Sir, quiz to syllabus is week 5 to week 9, no, sir?
Week 5 to week 8. There is no week 9.
Okay.
So till differentiability.
Okay, sir. Thank you, sir.
There is no critical point.
Yeah, 1 to 8, I guess.
1 to 8.
1 to 8 or 5 to 8?
Okay, we say 1 to 8 because you may not you shouldn't be like ये तो week 4 का है, V3. So that is why we say week 1 to 8. But more of we will give questions, direct
More
questions from
weightage
week
will be
5 to
placed.
8 only. See,
Okay, sir.
sometimes unknowingly inside some concept of polynomial or quadratic might be used, should be used. Then you
Right.
shouldn't be like this is not in the syllabus, right? So that is why we will say there will not be any direct questions from week 1 to 4. But within the questions from week 5 to 8, there might be some concepts merged into this from week 1 to 4.
Thank you,
Okay.
sir.
Yeah, thank you, sir.
Okay, I will look into this issue. Maybe I will tell them to upload it as soon as possible.
You will upload this
Can you
PDF
upload
also?
on Google and provide us link temporarily for until the portal gets updated?
So other than video, will you be able to upload the PDF?
See, that is what I am telling. I will send this PDF right now after this session. Maybe after 10 minutes, I will just send this PDF to get uploaded. Maybe they are, maybe, see, it's already 10:30, right? They will also take break. Maybe they will resume work by tomorrow morning 9 or sometime. Okay. So after 9, they will be like, they will take some 1 hour or 2 hours to upload. But I will constantly push them to upload as soon as possible.
We
That is
can
what I
watch
can
this
assure.
YouTube.
You can watch this YouTube also. But you will get the PDF, don't worry. I will ask them tomorrow is the deadline, bolke. I will do something and I will before 12 PM I will try to get this PDF uploaded. Okay.
Okay, thank you, sir. That will be very helpful. Thank you,
That
sir.
would be great, sir. Thanks a
Thank you,
lot.
sir.
Thank you, sir.
Thank you,
Nice
sir.
meeting you, sir. Thank you, sir.
Yeah,
Bye.
yeah.
Thank you very much,
Thanks.
sir.
Thanks.
Good
Say
night.
good night.
Yeah. Thanks a
Good
lot
night,
and
sir.
have a good day.
Thank you, sir. Good.
Thank you,
Thank you, sir.
Thank you, sir.
Right, sir.
I have to
Yeah.
go and cook.
One small doubt can I ask?
Mm-hmm.
In DFS, after in some questions, I have seen that they have given the tree diagram. From the tree, they are asking to draw the original graph. I was able
No. They will ask to predict the original graph. Correct?
Yes, options.
This is an important concept. So that is why I didn't start BFS today because it will take 1 more hour to complete.
So from original graph, I was able to draw the DFS, but from backward, I was unable to. I'm getting
See,
some.
for backward, you should understand few properties of this DFS and BFS first of all. So between two vertices, can I have an edge or not? You should understand. So for BFS tree, you can have edges between the same level vertices or one level above or one level below, not more than that. That is one property of BFS. So that is how you do the breadth first searching, right? So you will go explore all the neighbors. So if that particular vertex is coming in the 4th level or 5th level, then you are pretty much sure that there is no direct connecting edge with my root vertex. Sure, right? For sure. Because all the neighbors will come in the first level itself. First level itself in my BFS tree. So if it is coming in the 2nd level or 3rd level, then I am pretty much sure that those vertices will not have a direct connection. So like this, I can somewhat predict that a few edges cannot be possible and somewhat predict that few edges might be possible. So between these two, I will guess the graph. I can't actually get the graph, but we will guess the graph. This may be the graph or that may be the graph. We can guess using these properties. Okay. These properties and everything will require some time. Okay. I will ask the instructor to discuss this BFS and DFS in detail. Okay.
DFS and topological sorting. These three topics are left, right, sir?
Or else I have this BFS, DFS PDF also with me.
Can you please
It's
put
not.
Sir, can you take tomorrow's session if possible, like to continue?
Tomorrow I have stats 2 session.
Okay.
So yeah.
Can you
So that
please
is
put
why
in chat the link we can download?
link I don't have. I will just search. I have to search first of all. So it's last term's PDF. Okay. I have to search for it.
Actually, this 10th
Is
week
it
last
available
week.
in last term's portal, May term, like this
It
PDF?
should be. It should be. It should be.
Because I have access to both portals, September and May as well.
Okay, May term. I guess it should be. BFS and DFS I have
Where it
explained it
should be,
clearly.
sir? May I know the
It should be in
position?
the supplementary contents, notes,
Okay.
live session
Let me
notes or something, supplementary content.
10th week they have not uploaded, sir. Live
10th
section
week,
it's not there.
10th week, what they didn't upload?
Live section last.
Last term's live sessions they didn't upload.
So only I was unable to do this. I got confused.
Okay. Okay, I will ask them to upload. So we have sessions recorded last time also. I don't know why they didn't give. Okay, I'll ask them to upload.
That practice assignment one also. If we see the solution, we get some idea.
I understand.
So only graded is pending this week.
Okay, I will ask them to. I don't know why they didn't upload. They should upload this.
Sir, May portal is not available. They have removed the access.
Fine.
1 week back I can go with different ID, but right now it is not showing.
Okay, sure. No worries. I will check. I have to check my notes, and I will just, if there is something regarding this BFS and DFS, I will attach that also. Okay. Or else I will ask the tomorrow's instructor to discuss this BFS DFS for half an hour or 1 hour. It requires at least half an hour to discuss.
Yeah, we will remind him, sir. Yeah, we will
So
request
remind.
him to complete all three levels:
Just.
topological, BFS, and DFS. To explain first, then proceed.
Last week Thursday, if they have finished, it would have been nice.
Last week, what happened? I thought this is the second session for stat.
No, sir. This is the first section for this topic.
Let me discuss. What happened on Thursday morning then?
We waited till 7:30. Again, it's closed.
Oh, session didn't happen.
Yes, sir. This is the first session. So
Oh, then they will complement the session, I guess. Maybe on Wednesday we will try to arrange another session then.
we had to study.
Oh, but revision sessions and all going on now.
Okay, on 18th.
We will see. We will see what to do.
Let's postpone this graded thing. So
No. It's not possible. If it is possible, we would have postponed it way earlier. There is no need of asking at all. Okay. If it is possible, we would have pushed it. But it is not that possible. Okay. Okay, then have a good day. Bye.
Bye, sir. Thanks a lot.
Bye, sir. Thank you, sir. Nice.
Good night.